Ever wondered how a single accidental cable could crash your entire network? Well, welcome to the world of switching loops. Today I'm going to explain the spanning tree protocol simply, so you can ace your next networking interview. Stick around until the end, because I'll be sharing 3 common CCNA level interview questions and their answers. In networking, we love redundancy for reliability, but when we connect switches in a loop, it creates a massive problem. Without a way to stop it, broadcast frames will loop forever. This leads to what we call a broadcast storm, which can bring everything to a halt. These loops also cause unstable MAC tables and duplicate frames, making the network completely unreliable. That's where the spanning tree protocol, or 802.1d, comes in. It runs automatically on your switches. Its job is to block just enough redundant links to ensure there's only one loop-free path through the network. The best part? Those blocked links stay on standby, ready to take over if an active link fails. Switches coordinate this by sending special messages called BPDUS to each other constantly. The big idea is simple. STP turns your complex mesh of connections into a loop-free tree structure. It picks one switch to be the root, and then every other switch finds the best way to reach it. Step 1. We need to elect a leader, known as the root bridge. The switch with the lowest bridge ID wins. Your bridge ID is made up of 2 parts, a priority value and the switch's MAC address. By default, all switches have a priority of 32,768. If the priorities are tied, the switch with the lowest MAC address becomes the root bridge. Step 2. Every non-root switch must pick exactly one root port. This is the port with the lowest cost to reach the root. Cost is based on link speed. A slow 10 megabit link has a cost of 100, while a 100 megabit link is only 19. Gigabit links have a cost of 4, and 10 gigabit links are just 2. Faster paths always have a lower total cost. Step 3. On each remaining link, we pick one designated port to forward traffic. Everything else gets blocked. A blocked port stops the loop, but stays on standby. If a main link goes down, it can quickly switch to forwarding. Ports go through several states to prevent loops during changes: blocking, listening, learning, and finally, forwarding. Classic STP takes about 30 to 50 seconds to fully converge, which can feel like an eternity in a modern network. That's why we use RSTP, or 802.1w. It's much faster, converging in just 1 to 2 seconds. Let's recap the 4 key takeaways. 1. STP prevents switching loops. 2. It elects a root bridge based on the lowest bridge ID. 3. Switches find the lowest cost path to the root. And 4. RSTP is the faster, modern version you should use. Now for those interview questions. Question 1. If 2 switches have the same priority, how is the root bridge elected? The answer: the switch with the lowest MAC address wins the tiebreaker. Simple as that. But be careful. Older switches often have lower MAC addresses. Always set your root switch's priority manually to stay in control. Question 2. A switch has 2 equal cost paths to the root. Which one becomes the root port? We use tiebreakers in order. First, the switch looks for the lowest upstream or sender bridge ID. If those are also tied, the switch picks the path from the neighbor with the lowest sender port ID. Final question: why does RSTP converge so much faster than the classic version? RSTP uses a clever proposal and agreement handshake instead of waiting for passive timers. It also uses edge ports that forward instantly and keeps backup roles on standby to take over immediately if something fails. I hope this made spanning tree a lot clearer for you. Did you get all 3 questions right? Let me know in the comments. If you found this helpful, please hit that like button and subscribe for more networking basics. See you in the next one.